to talk a little bit more about how it works. How does the LiDAR work? Okay. So what are the components of a LiDAR system? Well, there's four main components. There's a laser scanner. There's a GPS. There's an inertial navigation system. There's an onboard computer. And I'm going to talk about each of these a little bit separately, so you get a sense for the role that they have to play in the system. Next. Okay, first of all, there's a laser scanner. This, of course, is the most important piece of equipment, and it's important to appreciate what makes a laser different or unique from any other type of electromagnetic energy that we might use. Okay, LiDAR is an active system, so it's actually sending out, it's actually generating its own electromagnetic energy, it's sending it out, and that energy is interacting with the terrain and then being returned to the sensor. Okay, and that energy comes in the form of laser light. Okay, and laser is also an acronym. The acronym is here. We don't need to be so concerned with what the words in that acronym mean. But what's important to understand is what makes a laser a laser. Okay? Now I'm holding a laser in my hand, right? A laser pointer. You've all seen them before. Okay? And they have three important characteristics compared to any other form of light that we might be used to. First of all, they're monochromatic. That is, they're one color. You can see that in this case, it's red. Okay, it's single color. Lasers are coherent. Okay, coherent meaning the waves are all in phase. You can see that here. These waves are all in phase. Okay, compared to another light source where the waves are all out of phase. Okay, if we think about a flashlight or a torch, okay, and shined it on this screen, it would look much different. Okay, and that's as a result of the fact that the waves are out of phase. And there are many different colors. And finally, these waves are parallel to one another, as you see here. So, in short, it's a very focused form of light. Okay? That's important because it's what makes LiDAR work the way it does. Okay. Now, for topography and forestry applications, that laser light tends to be in this infrared wavelength. Okay, there are lasers, there are LiDARs that operate at other wavelengths, but this is the wavelength that LiDAR tends to operate at for forestry applications. Next. Okay. The next component of the scanner gets at how exactly it works. Okay? You can imagine we have an aircraft like this one. It's flying along. Okay? And it has a laser pointed down at the ground. Okay? Now, the laser itself does not move back and forth. Okay? Sweeping the ground. It doesn't work quite that way. Because we don't want to move. This is a high-tech piece of equipment, and we don't want it moving. Okay? If we can help it. That just could lead to problems. Okay? So instead, what happens is, instead of having the laser move, a mirror is used. Okay? And it's the mirror that moves. The laser is stationary. It points at the mirror. Okay? The mirror moves in a particular pattern. And when that mirror moves, it creates the patterns that you see on the ground. Okay? And the mirror can move in different ways to produce these different acquisition patterns. Okay? And if I were to shine this laser at this mirror, holding it still but move the mirror, you can see what I mean. Okay? So it's the mirror that moves, not the laser. Next. Now, it's very important, very, very important, in fact, that we know at all times exactly where the aircraft is. Okay? Because if we know where the aircraft is in space, and we know its position in space, then we know where the LiDAR returns are coming from on the ground. But if we don't know this well, everything else falls apart. Okay? So there are two things that we need to know where the plane is in space and its position. The first is GPS, which you're all probably quite familiar with. All right? There needs to be a GPS reference station with line of sight to the aircraft at all times when it's flying, so that we know where the plane is. Okay, next. The plane itself, however, needs to also have an inertial navigation system on board. Well, what is that for? Well, as you can imagine, as a plane is flying, it's being buffeted by the wind, right? It's not perfectly still. So we need to know the position of the aircraft at all times. And it's an inertial navigation system that provides those measurements of roll, pitch, and yaw, okay? The exact movements of the aircraft. Okay? Next. Of course, there needs to be an onboard computer to put all this information together. The onboard computer records the returned photons of laser light, keeps track of the laser timing, keeps track of the angle that mirror is in at all times, records the GPS info, records the inertial navigation system info. It takes all of this and it converts the returns, the individual point returns, into X, Y, Z coordinates. Okay? Remember those point clouds I showed you earlier? We need to have an X, Y, and Z coordinate very accurate with each of those. And then, of course, it provides a real-time output display. Next. So, how exactly does it work? Well, it's really very simple. A LiDAR is just a tool for measuring distance, really. Right? And distance is measured by estimating the time it takes for a pulse of laser light to travel from the sensor to the target and back. Okay? And we need to know the speed of light for that. And because the distance is in two directions, down and back, we need to divide by 2, and we can get a distance measurement. If we know this distance, we can begin to measure the heights and structure of what's on the ground. Next. Next. Right, great. Okay. So, how are these returns recorded? Well, you can imagine the plane is flying, the laser is pointed at the ground, it's scanning using that mirror. Pulses of laser light are encountering targets on the ground. Could be trees, could be buildings, could be other structures. Okay? When the laser light encounters something, it's reflected back. Every time it encounters something, it's reflected back. All right? And the positions of those returns are recorded. The X, Y, Z positions of each return are recorded. All right? And it's those returns, when we put them all together, it forms that point cloud. Okay? Next. Here's our point cloud, right? So, all of these points are just as a result of those individual returns being recorded, and we have X, Y, and Z positions of each of them. So LiDAR data is actually very simple. It's really just millions and millions of points where we know exactly where they're from. But when we put them together, we can begin to see very interesting and very useful patterns, particularly when we're talking about forestry applications. Okay. Next. Now, in the previous slide, we were looking at just 2 trees in the middle of the field, right? Well, this is an entire transect from a portion of the Yucatan Peninsula. And this is the point cloud that was collected. Again, this is displayed such that the tallest features in the image are red, the lowest features are blue. So ground is blue, tops of the trees are red, everything else is in between. You can see forest, okay? You can see a street, individual buildings, you can see a power line, you can see open areas, you can see a variety of different things. In great detail, okay, you essentially have a 3D representation of the landscape where the LiDAR was obtained. All right? And as you can imagine, the power in this is taking this point cloud and extracting useful information from it. And what the balance of my presentation is going to focus on is how we, as part of our work, have extracted information, forestry relevant information, from point clouds like this one. Next.
Sorry, I have a question.
Yes, of course.
If there is a lake in the middle of that point, also looks blue. For example, if there is some lake.
Yes, it would look, well, as I've represented it here, it would look blue. Because using this color scheme, it would have 0 elevation. But in general, yes, it would look like everything else at the surface. That doesn't mean you can't separate it from everything else. There are potentially ways to separate a lake from the surrounding surface. Okay. Okay. Now, we're going to spend today talking mainly about forestry and forest management applications, but it's important to appreciate that there are many, many applications of LiDAR. And when you look at one of these point clouds, you can begin to think about how many different applications there are, because there's so much data contained in this point cloud. LiDAR is being used for atmospheric measurements. It's being used to monitor glaciers and ice sheets. It's used to produce digital elevation models, looking at risk from landslides. There's all sorts of applications related to the hydrosphere, looking at water surface roughness, turbidity, shoreline and coastal change. There are urban applications in terms of urban planning. It's being used increasingly by archaeologists to identify, for example, beneath forest canopies, archaeological sites. And in fact, in some of the data that we acquired here as part of the MRED project, we found areas where if you just looked at the point cloud itself, you wouldn't see anything. But if you strip away the trees, you see structures beneath that are archaeological in origin. But obviously today we're focused here on the biosphere, particularly on vegetation, forest inventory, forest structure characterization. So that's what I'm going to be spending the rest of my time on. I'm going to be talking more about this, but there are many, many different attributes of forest structure that we can extract from LiDAR point clouds. And many of them we can do very, very accurately, more accurately than we can do with any other data. Whether it be biomass, basal area, canopy cover, tree height, stem density, ground slope, all of these are possible. And again, when you see these point clouds, it's not surprising that this can be done quite well with LiDAR. Next. All right. So I'm going to shift gears a little bit now. I'm going to talk more specifically about our MRED LiDAR initiative and potential applications of these data and data like them to the work that you all are doing here in Mexico. Next. Next. So just a brief outline. I'm going to first talk about the MRED LiDAR initiative. I'm going to talk about some of our accomplishments to date. And then I'll wrap up by talking about potential future applications to forest measurement and monitoring. So first, the initiative. What did we actually do? Well, let's present the timeline. In July 2013, Carto Data was awarded a contract through the MRED project, which is a USAID-funded project to acquire airborne LiDAR data at sites across the country. In December of 2013, the acquisitions began over Jalisco. The acquisitions continued through May of 2015. Took quite a bit longer, I think, than we expected because the acquisition team encountered a lot of challenges. Some of them had to do with weather, okay? LiDAR has to be flown when the weather is good. You don't want to fly LiDAR when there are low clouds, when there's rain, when there's anything that the LiDAR pulses might encounter on the way down to the ground, okay? There are also issues in terms of ground access in a number of locations. As I mentioned earlier, we need GPS line of sight to the aircraft at all times, and so a team needs to go out on the ground with a GPS receiver to collect that data, and in some parts of the country, access, of course, is difficult. So there were issues, and it took longer than we thought, but in June 2015, the completed data set was delivered. Next. All right, so now I'm going to take you through some of our accomplishments, all of our accomplishments really to date, where the LiDAR data is concerned. And the first one is that, of course, the acquisition was completed, and it was completed following input from a broad range of stakeholders. Government, including groups like yours at Kona 4, academic institutions, local NGOs. We wanted to pool everyone's thoughts together on where we should allocate our resources in terms of acquiring these LiDAR data. Okay? And I'll talk a little bit more in a moment about some of the criteria that we were interested in related to where we put these specific sites. But it was important for us that we heard from everybody, because obviously we only had limited resources and we could only do this once. So we wanted to do it well, or at least as well as we could. So this is what the MRED LiDAR acquisition looks like. These black lines and black quadrants represent the actual acquisition, the places that were flown. Overall, 1,685 square kilometers of data were acquired through this effort. How did we go about identifying these particular locations? They seem to be sort of spread out, and they don't appear to have any real rhyme or reason to them. Well, first of all, we were interested in flying over existing locations where existing field data could be accessed, okay? So that includes INVIS plots, that includes other state-level forest network plots, that includes ecological field research plots, any place that we could fly where there was relatively current, relatively accessible field data that we could bring to bear on calibration and validation activities, okay? So we talked to folks who were willing to share data. We also wanted to ensure that the acquisition was representative. What do I mean by representative? Well, we looked at layers of biomass, we looked at layers of forest type, we looked at layers of elevation, biodiversity, a number of different GIS layers to try to get a sense for the diversity of ecosystems in the landscape, and try to see how we could best capture those representatively with the LiDAR. We obviously had limited resources, but we wanted to do our best to capture as many different types as we could while ensuring that we were flying over places where data was accessible. So a number of different criteria, and it actually took us quite a bit of time to put this acquisition plan together, but I think it was a really good process, and it was a process that we were proud to undertake. Next. Now, it's important to appreciate that the MRED LiDAR acquisition was not the only acquisition made in Mexico. There were several others, actually, some large and some small. The other large one was acquired a couple of years earlier around 2012 by NASA, and it was called the NASA G-Lite sensor, and those flight lines are shown in blue. So you see the CartoData flight lines, the MRED flight lines are in black, the NASA G-Lite flight lines are shown in blue. So you can see when we put the two together, we have pretty good coverage throughout the country of the range of forest ecosystems. There are also other acquisitions that have been made, smaller ones, including one out here in Baja that we actually don't have access to, at least not yet. We hope to one day. I believe it was sponsored by the U.S. Forest Service. Eventually, we'd like to put all of these acquisitions together so that the community can make use of them collectively. Now, what you see in the background here is the distribution of conifer, INFIS, and forest management plots. You can see there are many, many plots, as you all know well, across the country. You can see the distribution of the LiDAR acquisitions relative to those plots. Now, obviously, in total, there are thousands of plots out there in the landscape. Of those thousands of plots, 671 fell beneath the two LiDAR acquisitions, the MRED CartoData and NASA G-Lite, okay? 671. Keep that number in mind because it's going to come up a little bit later on in the talk. Next. All right. The next accomplishment had to do with designing and implementing a data sharing platform. One of our objectives from the beginning was to make this data publicly available. Next. So we developed, as part of MRED, a spatial data sharing platform, the link which you can find here, where you can go and you can download these LiDAR data. Next. This is just zooming in on the Yucatan Campeche region acquisition. The LiDAR data set is divided into individual 1 kilometer by 1 kilometer tiles to make it easy to access. And I'll talk a little bit more about that in a moment. Now, the G-Lite data, the NASA G-Lite data, is also available online at this location. It's also available to the public. Okay. Now I'm going to talk about what we've done in terms of making the raw data and the derivative products available to the community, to the world. So coming back to this initial acquisition, okay, 1,685 square kilometers. Let's focus here for a moment in the region of Chihuahua. And we're going to next. We're going to take a close look right here. Next, if we zoom in, you can see the individual 1 kilometer by 1 kilometer tiles that are available online. Next, and we can see. And this is actually the online interface. We can see that there are a number of different data types available. Okay, for those of you that know GIS and remotely sensed data, you'll recognize some of these data. We've made available both the digital surface and digital terrain models. For those of you who don't know what those are, I'll explain them more in just a moment. We've also made available the hillshades of the surface and terrain models. And we've also made available the raw data. The raw data comes in a format called LAS, L-A-S. That is the format that contains the raw point cloud data. Next. Okay. So, there, yeah, thank you. So I want to give you a sense for what these data look like. Okay. This is a digital terrain model, and by itself, it doesn't look like much. You can see a little bit of variability here. You can begin to see some river valleys and some hill slopes. Okay, but it's kind of hard to get a good sense for what's there. Next. However, if we display it as a hillshade, which again, those of you that know GIS know what a hillshade is, we're essentially applying some shadowing to it. You can see what the terrain looks like in this particular region of Chihuahua. It's very, very diverse. Next. Now, this is the digital surface model. Now, if you recall the digital terrain model from 2 slides back, it looks virtually identical, all right? Doesn't look very exciting. But what makes the digital surface model different from a digital terrain model? Well, in the case of terrain, we're just looking at the bare earth. We've stripped off everything on top of it, including trees, including structures, everything removed, just the bald earth surface. Next. The digital surface model, however, leaves everything in. And here you can see this speckle pattern is actually due to the individual trees on these hill slopes. Okay? Now we're going to zoom in a little bit right here. Next. When we were collecting the airborne LiDAR data, we were also collecting orthophotography. So this is the ortho photo of that region. You can see there's a river valley. There's forested hill slopes on either side. Next. Here is the terrain model. Now this is the bald earth model, no trees. Next. Here is the digital surface model. These are all individual trees. You can even see power lines. All right, and if we apply a color scheme to it, we can see taller trees in green, shorter trees here. These are orchards or small plantations in this orangey color. As I was mentioning, we can see power lines. We can see individual structures down here. You can see a lot of detail. You can almost, in this relatively sparse landscape, you can almost count the individual trees. Next. Okay. Let's take that same area and look at it in perspective point of view. This is that river valley that we were just looking at. Now, this looks like an orthophoto, all right? But it's not. It's also a point cloud, like the first slide I showed you in Oaxaca. This is a point cloud, all right? It's made up of 225 million points, and this is only 2 kilometers by 2 kilometers. So even this small area is a very large data set, all right? Now we're going to zoom in onto a region right here. All right, before we zoom in, we can display this point cloud in different ways. We can display it in terms of elevation. The elevation here ranges from 2,141 meters to 2,587 meters. Here are the lowest areas, of course, in the river valley, highest areas on top of the mountains. Next. We can also colorize it in terms of just forest height, tree height. From 0 to, in this case, about 40 meters, you can see the tallest trees growing in some of these moisture valleys. Now we're going to zoom in. Go back one. We're going to zoom in right here to a portion of this slope. Now this is about 40 meters by 40 meters, a relatively small area of the slope, and you can actually begin to pick out the individual conifers. You can see their shapes. All right, again here, 0 to 23 meters in height are these trees, and you can see they show up pretty well. You can almost count them in this point cloud. 200,000 points making up this relatively small, roughly 40 by 40 meter region. Next. Okay. One more. No, one more forward.
Okay.
Sorry. Yeah, okay. Now, I want to switch gears a little bit, and I want to talk about how, as part of our research, we're using these data. How are we using these point cloud data to generate useful products, to generate useful information for forest measurement and monitoring purposes? Okay, what is our strategy? Well, first of all, I want to talk a little bit more about our philosophy, if you will. Oftentimes, what we're confronted with is a case where we have relatively sparse field measurements, okay? Let's think about the INFIS for a moment. The INFIS system is very robust, all right? As we saw in one of the earlier slides, we have plots, thousands of plots spanning the entire country, okay? But we also know how difficult it is to implement and maintain a system like that. Okay, it's very expensive. There are plots that are very difficult to reach. There are plots in remote locations.